Today we have a very special guest, Pascal Paillier. It's an honor to have him here today.
Thank you
Paillier
for
has made a quite significant impact in the cryptography world. He's known for the Paillier crypto system back in the days, and I'm sure I've heard of this term and learned about it back in high school. And many will also say that Paillier is one of the co-inventor of FHE, also godfather of this entire cryptography. So it's really an honor to have him here today. And
Thanks
today we'll
for
get to
having me.
learn Pascal a little bit more, kind of like what motivates him, and then
Yeah,
what led him to his vision for FHE.
yeah. Well, again, thanks for having me. It's a pleasure to be with you. And I was saying before, a pleasure to actually discuss FHE with people who actually implement it and deploy it and advance it in a way or another. Um, so initially, I think the idea of FHE came back to the late 70s. This paper by Ron Rivest about privacy homomorphisms, and like a lot of ideas in modern cryptography, it was mainly like a concept with little mathematical evidence to support it. But there were like hints or like intuitions that it could be built maybe. And in the idea of privacy homomorphism, you can already see the idea that at the time people were looking at modular exponentiation. So, Diffie-Hellman, key exchange, and so on. So you have like G to the A, G to the B, mod P. And I think the idea behind creating FHE with that, we know today that it cannot be built just out of this. Or maybe we missed something major, but I don't think so. Like very pessimistic about that. But the idea was, okay, what if we could encrypt a message by just using it as a power? Like, so if you have generator G, mod P, and you do that G to the message, mod P, and then given an encryption of M that way, you multiply an encryption of M1 with an encryption of M2, you can already add them because everything is happening in the exponents. And the idea was, maybe, with Diffie-Hellman, where you have G to the A and the other guy has B, and he raises G to the A to the B, that gives J to the AB in the exponents. So there's kind of a product there. And the intuition was, what if, without having to know B, I can create J to the AB from J to the A, J to the B? So if you put that on top of the previous idea, that would give you a way to kind of multiply plaintext through encryption. And so at that point started the idea of putting a kind of a backdoor in the discrete log. Like you could take a message, raise it, take the generator, compute G to the M, mod P, or whatever, similar structure, a cyclic group or something. And then you would have like a backdoor to retrieve easily the exponent, like to break the discrete log. It was I think the main idea that actually created the first part of the history of FHE. Like it was mainly about putting backdoors in the discrete log. It was that for decades.
Was there like a context back then to re-explore this direction, in your opinion, back in the 70s? Because that's also almost pre-modern computers, right? Or internet.
Yeah.
So
Yeah.
fairly early. Do you think back then there were some, interesting context about this direction?
Context in the sense of if people had, I don't know, found a way to have FHE at the time, would it
Yeah. So I guess
have become a successful technology and business at the time?
yeah, were there specific needs in terms of like solving this problem back then, or was it just more of a interesting
No,
exploration?
I think it was like like wishful thinking. Like people
Got
were
it.
dreaming about it. I think it was the time like 70s, the 80s, where people started to build the modern concepts in cryptography. So everything about zero knowledge came about in the 80s. Yeah, when people discover zero knowledge today, it's like it does something to me.
Yeah.
There's a whole, past and backlog of ideas and discussions and like scientific debates about what is achievable, what is not. Like, but yeah, certainly now, there's it has transformed completely. Like it's more about compilers and more about circuits and deploying and efficiency, which is very good. It shows the maturity of the field. But it was the case for plenty of other ideas, like even public key encryption was revolutionary, like in the 70s, and there was also the other concepts like everything, like one-way functions and like the kind of a modern grasp on these concepts in a way that make them instrumentable mathematically. You can reason about them. You can prove like hierarchies of properties, and it was, I think, the first time that people started to really build modern cryptography. There was obfuscation as well. Like all these concepts date back to early cryptographers, like obfuscating a program, which in principle you should ask, like, what is the connection with cryptography? But at the time there was no frontiers. Like people were trying to consider like seemingly paradoxical problems, and they were trying to crack them any way they could.
They were mostly just having fun, exploring different things.
Absolutely. And reading papers was much easier as well. Like
maybe the question is, take us back in the days, right? Like, what was the community, the scene of cryptographers? How was that like? So for any new papers, right? How did you come across these new papers? How do you get connected to other cryptographers? Like, how was it back in the day?
Okay. So there are several back in the days. So my personal back in the days was I started cryptography like in '96. So,
okay.
Like the older generation. I didn't get to code when I was a kid because computers weren't there yet, and they were like too expensive. And so, but I was doing electronics, which was the thing in the '80s. Like people, like smart, kids would play with electronics before they would play with computers.
How does that work? I don't even know what electronics is.
You didn't know that?
No.
So at the time, the Silicon Valley was not about computer science,
and
computers. It was about electronics. And so it was the early days of computers, but they were like too expensive, and they were starting to find their way to homes, but it was like the beginning of it. But what was like super cheap was electronics, and you could buy a few, buy some equipment, and as a kid you would build like circuits. So, and they were like, at the time there were like magazines, even in France there was like magazines where in the magazine there would be like pieces that you can assemble to create your own circuit.
Interesting.
And so I would buy that like every week, and I would how do you call that in English? Like the iron.
You just iron the tool.
I don't remember, but you would put like tungsten in there.
I know
it would
you're
melt,
about.
and you would create like connections between the wires and everything. And so it was like that for me. And I would create like I don't remember, like a radio, a phone. I actually wiretapped my phone line in the home in my house with a tape recorder, so it would record like systematically every call.
Oh, that's
it
super
was just to bother my parents.
That's super interesting. Yeah.
But so when I started, I think I started to code really. I think it was like 14, 15.
Okay.
And it was in BASIC and pick, pock, go to 20, that kind of stuff. There wasn't much you could do at the time, right? It was I think my first program was music. It was doing music or something, but it was so poor
making
compared to today.
Electronic beats.
Yeah, exactly.
Okay.
Yeah. Huh. And there were so many. I mean, there were not that many sounds you could play with a computer. Like, it was ridiculous. I mean, but it's only. But I was like very good at maths, and I was more like on a theoretical side of things. But yeah, and of course, when I started like programming, it was another game, and I was like in my 20s, and it was like a fantastic discovery. And also, I was about to become a physicist,
Okay.
And I suddenly stumbled upon a little book called Cryptographie Contemporaine by Gilles Brassard. It's actually Canadian. And it changed my life because I discovered cryptography.
Okay.
And he was like describing these techniques with commitments and zero knowledge, and how to play, how to toss a coin by phone, this kind of stuff. And I was like,
Just like
I don't know,
magic.
it was mind blowing
Yeah.
to me. So I decided to stop studying physics, and and yeah, I was doing mathematics at the time, and I kind of integrated. In France we have this dual system between universities and grandes écoles.
Yeah.
And so I went to applied to a grande école, and where I knew there would be somebody who was like doing cryptography, and this guy who was teaching cryptography there and coding theory actually became my PhD advisor after that. And yeah, and then I started an internship in a smart card company called Gem Plus at the time, and I met my mentor, who was like David Nakash, fantastic human being, fantastic both scientifically, human skills, also a fountain of ideas and motivation. So that really gave me, working with him really gave me kind of a super motivation to really, make a difference with crypto.
Yeah.
And immediately I was like coding on smart card chips. So basically at the time, the first thing I did was in assembly code, I would develop like a symmetric encryption algorithm for GSM, for telecommunications in Hong Kong or something. So you would be given the specs, and you would have to code that basically in assembly, like 8051 or 68 HE05, that kind of like Motorola or Intel chips, and 8-bit chips. So smart card industry was like way behind in terms of, because of power consumption, right? So that's the first time that I started like implementing cryptography. And I always kept this like motto that David had, still has, which is, if you don't understand something until you implement it. When you implement it, it becomes like way more clear of what it is.
Yeah. I can relate to that. Yeah. Even in software engineering, sometimes
in general,
you can build it, but it's until you build it you actually learn.
Exactly. Yeah, exactly. So so these were like the early days for me, like cryptography. I started doing a PhD, and I started spending my nights developing cryptographic libraries for smart cards, and I loved it. And today it sounds ridiculous because you don't have like memory constraints, or but back in the days you had like 256 bytes of RAM.
Oh wow! So you have to think about the constraints and design around it.
And you have like a crypto accelerator, like an arithmetic machine to do like large integer modular arithmetics, and would have to find a way to like program a DSA or an RSA signature, and you would try to save like every possible byte or every possible running time. Eliminate as much as possible to make it
feels
fit on this.
Very similar to how you program smart contracts today. You have to be optimized.
Yeah, exactly.
Every single line.
Exactly.
Of code.
Exactly. But after that, things evolve, and then suddenly you have like a lot of memory, and it changes the relationship between the developer and the code.
Yeah.
And also the thinking that goes along with the coding. It's a different thing when you can find a lot of very inspiring problems by trying to code something in extreme circumstances, like memory constraints or time constraints. And it would make you like discover tricks, like mathematical acrobatics. And it would be very like inspiring, and So it was like that for me. Like I would like work on that, and then yeah, homomorphic encryption was. I think no one was really. I mean, there was like other people who had explored the idea and tried to build this backdoor in the discrete log. So there was like I don't know, half a dozen papers or constructions, and Josh Benalo, he made his PhD on that. He was using that to do electronic voting at the time. So he was in the 80s, I think, if I remember correctly. And he basically used the addition to kind of compute, to tally the votes. And so you would encrypt the votes, and you would like addition to tally them all to get the tally, and then that was the idea. So he was like motivated in building like the first backdoor in the discrete log. He did that in a way that was like refined by later papers, and I found myself like fascinated by this idea. So I was like looking at other papers, and then I went to Eurocrypt, boy, 98. And there was the Okamoto Uchiyama paper, which was like the first really kind of efficient backdoor in the discrete log.
Okay.
But it was kind of broken. And so I remember going to a Russian restaurant together with David and the team that we had. We were a team of cryptographers. And I had, I don't know how, I don't remember how it came about, but I was writing on the table, and I was preparing that Okamoto Uchiyama construction, and the presentation had been like earlier that day, and I was like repairing it, and David looked at that and he said, "Oh, meh, okay, maybe you can try to publish that." And I said, "Okay." So I kept the idea, and it's only when I started like digging around it that I saw that it was like the best scheme at the time to do like homomorphic addition. So I took the energy to write a decent paper about it, like pinpointing the properties, doing the security proofs, and trying to make a proper work that people could build on. So I did that, and after that, yeah, a lot of people started to use it as like the state of the art for addition. But yeah, at the time it was like building addition properly and doing it in a clean way and as efficiently as possible.
Was that the first actual implementation of HE that was, practical, that actually worked?
I would say yes, because because the previous constructions were, to my knowledge, never really used or never like implemented, and there were like possibly like a few prototypes or stuff like that, but when I published the scheme, I saw like a lot of people like starting to use it like right away, like
I think your paper was quoted more than
protocols.
9,000 times. Definitely had an impact in this space.
Yeah. And then I started for years to do fully homomorphic encryption, not just addition, but it was like super hard and super.
So regarding HE, you mentioned voting. Was that kind of like the major use case?
Yeah. Okay. It was the main motivation. Yeah.
Okay.
If you look at Josh Benalo's PhD manuscript, it actually never, I think, mentions any other use case than voting. But at the time, voting was one of these like things that we wanted to have solutions for.
Yeah.
So it was, I think, the main motivation. But when MPC came about, HE just became like a natural ingredient to build like larger protocols to do other stuff. And it wasn't just voting anymore. But it was like voting was like the go-to application, the use case that you would mention in the introduction of your paper.
Interesting. So HE was sort of a precursor to MPC because it's a major component.
Yeah, it definitely, I think it gave MPC a big boost. Yes. And also you can actually, I mean, secret sharing typically is also homomorphic. it's hardly a notion of encryption because there is no key. There's just distributed shares, but it's kind of similar in the principle. And so homomorphism is basically the property that you need when you build protocols. It's
Yeah.
yeah. So it was just only like FHE, but like the homomorphic properties of the MPC operations.
Yeah.
Yeah.
So I guess I'm curious. So after your paper came out, did the landscape change? Like how did it, develop afterwards? Because I'm sure a lot of people started to pay more attention into this space, right? Um, so yeah, between 1999 to the next generation of FHE schemes,
Yeah. Yeah.
yeah, how did that, how was that landscape?
So the landscape was anytime people would refer to homomorphic encryption, they would refer to my scheme. Also, my name. I should have. In crypto, usually you give names to mechanisms, especially like in like symmetric key crypto. Like we have like mechanisms like called serpent or tiger or and in public key you don't really do that, or you do that like sometimes. And this was a public key construction. So if I had given it a name, it would be known as like the Paillier crypto system. But I didn't do that. I didn't even think about it. And then it's like super weird when you see people referring to the scheme with your name.
Yeah.
It became like a very, very cited crypto system. There were actually a main crypto system and two other variants. And so people were like selecting which, the crypto system that would best suit their needs. And it was funny to see that, but people elaborated upon these mechanisms. So they made it like they thresholdized it so that you can do threshold decryption with it, zero knowledge with it. Also, they were like a little bit more intricate variants of it to optimize performances. So it was used like in kind of every flavor, like strawberry, raspberry, or so on. But it was like normal. It was like using it like as a basic building block to build some like auctions or whatever. Like in papers, it was like mainly about solving a certain problem, and homomorphic encryption was just a small like ingredient in there. Like it was just a means to get there. And I think that was like the vision of homomorphic encryption, like an ingredient, until 2009 and Gentry's kind of initial like construction, which was eye-opening to a lot of people, including me. And that was, I think, when really FHE started to become a thing. Yeah. It was a defining moment, I think, for cryptographers. Absolutely. There were like other moments, like zero knowledge was a big thing also in its time. But I think it's like, there are critical moments there where science is happening. Like suddenly you have a big boom in ideas.
Some inflection points.
Yeah.
Some breakthroughs.
Yeah, absolutely. Yeah, especially the idea of, but it was like very different. Like FHE suddenly was achievable, but with like different algebraic context, using lattices. Or not only you can actually, there were examples of schemes like GGHV that actually use like modular arithmetics, and you don't need any mathematical notions outside of modular arithmetics to understand it. But there was this discovery of several traits of FHE, like there must be some noise, which was like, but there's noise, yeah, but the noise grows, yeah, but if it grows too much, you lose the consistency of the computation.
Yeah.
And that was new. Like before, the crypto systems were like very clean. So you could do like you could do stuff, but there would be no notion of of noise growing. It was like very annoying in the beginning because we weren't used to that notion of there is a danger and it's coming to grasp your message and actually flow over it and destroy it. And it was like, what? And but then, of course, cryptographers being cryptographers, there was, it's the science of solving paradoxes. And so they came about, they invented this notion of bootstrapping, which allows you like to clean the noise, and that was it. You can encrypt forever, compute forever, and conceptually, and then it became a question of improving performances and stuff. But what is very interesting, because in retrospect there were a lot of ideas around FHE, and in retrospect you can kind of build some filiation between these different ideas. But if you look at this graph that gives you, is still a spaghetti dish. It's still plenty of ideas popping up. And, GSW was another like conceptually different idea to encrypt. Nothing to do with previous idea, but I found it like very interesting, very beautiful. It uses eigenvalues and matrices. So the thing you do is a ciphertext is a matrix, right? And your secret key is an eigenvector, right? So if you decrypt, you apply your secret eigenvector to the matrix. And because it's an eigenvector, it goes through the matrix multiplication. It gives the vector itself, multiplied by an eigenvalue. And then this eigenvalue is the plaintext. And so when you decrypt, you just apply your secret vector. You get the secret vector itself multiplied by your scalar. This gives you your message. But with the beautiful property that if you add two ciphertexts, when you decrypt, this gives you the addition of the two eigenvalues. And if you multiply the two matrices, because it's an eigenvector, it goes through them all, through the two matrices, and that multiplies the eigenvalues. So that was like the natural concept, how to kind of build, an FHE system. And unfortunately, like it's very, very inefficient. So they had to kind of, this beautiful concept was kind of lost in translation in what came after, which was like trying to improve the efficiency by any means. But there are plenty of ideas like that suddenly appeared in the field. And maybe one day we'll be able to get rid of the noise. That would be like
completely.
Maybe. I don't know. I'm not like super optimistic, but apparently Dan Bunny has ideas about how to do that. And he asked us at Zama if we would be interested if he finds a solution by using it. So of course we said yes, of course. And without the noise, actually, there would be no bootstrapping. So probably you could do operations forever without having to mind how to build a circuit or something. It would be so
it'll be game changing.
Nice. Yeah.
So I've heard Gentry, I think previously worked with Dan Bonnet, or have you guys previously collaborated as well in the past in terms of research in this space?
I never wrote a paper with them.
Okay.
But I knew them, of course. Yeah. I met Dan, I think, the first time when I was working in the smart card industry. He kind of, it was in 97, I think. He published a paper, How to Attack Smart Cards by Injecting Folds. And it was a big thing at the time. Like you put the smart card chip under stress, and you make the CPU, the arithmetic and logical unit, create a mistake, like a transient error. And you can submit the chip to, I don't know, UV light or extreme temperatures or whatever. And there is a secret key in that chip. And you try to mathematically infer the key from a faulty response.
Oh, super interesting.
Yeah.
It sounds very similar to like an SGX attack.
Exactly.
Yeah.
Exactly. Secure enclaves are coming from this world of having like secure computing.
Yeah.
And in the early days, well, like smart cards. I think smart card, now the technology has become completely obsolete because of phones. But everything that has to do with securing crypto implementations, not only like schemes,
Yeah.
constructions that have a security proof, but when you implement actually these schemes, you can have like attacks on the implementation itself. And RSA was under attack, GSA was under attack, and so it was a whole area. And Dan was actually working on that. I was on the other side trying to find countermeasures, and yeah, and so we would kind of discuss that in conferences. But it's all actually in conferences, people are very nice to one another, especially in cryptography. I mean, people are nice. There may be a couple of divas out there, but essentially people are nice,
Yeah.
And even though sometimes they fight academically or they're not on the same side, but it's yeah.
Yeah, very cool to see that. And I guess like making bootstrapping more efficient. So I guess we can talk more about how you and Ren met and then decided to start Zama.
Yeah.
Because I really believe what you guys are doing is
Yeah.
really solving a big problem, making this
Yeah.
a lot more efficient.
Yeah. Yeah. So I met Rand in 2015. So at the time he was like heading SNPs, and he was also he was always like super obsessed with privacy. But he was coming from the ML side of things, and so it was more. So at the time, SNPs was like trying to put like models in embedded environments like chips, and to avoid having to deal with the Alexa scenario where everything is uploaded in the cloud and then processed there, and then you have no privacy whatsoever. And so I was on my side. I was so I created a company in 2009. I basically took my team at Gem Plus, who had become Gemalto in the meantime, like the number one like smart car company, and we were kind of fed up of working there because like would be a team of kind of advanced cryptographers. So we would find ideas, but also not only like technical ones, but business ones, how to build like new services, new products, and fight patents all the time. And it was really disappointing because the marketing people or the people in the company would do nothing with our like outcomes and findings, and it was very, very annoying. So we decided to become like an independent kind of small company. So we created Crypto Experts. We didn't have a name for it, so it was always like the Crypto Experts idea. So when the day came that we had to find a name, it was like Crypto Experts, and it still exists today. But we kind of became independent and would be a consulting company and doing also like private research for companies who would not necessarily have like in-house expertise to conduct projects. And at the time, so I was working on FHE and especially TFHE and trying to elaborate on the bootstrapping in TFHE, and so I was working on the PBS idea, like the programmable bootstrapping idea, and work out the equations to increase the precision of the plaintext, and also what can you do with it. And I think that was something that was nascent in the TFHE papers, but it wasn't an idea that was like elaborated upon as a means to do homomorphic circuits. So I was working on that, and I at some point, so I published a couple of research papers, crypto that year, and I reached out to Rand. So that was like 2018, 2019, beginning of 2019, and with Rand we had like conversations about FHE. Was interested in FHE back in 2015, but there was no way. I mean, at the time, it was too inefficient. So, but he always like, this idea of having like efficient FHE was something that was resonating with him like very strongly.
So you knew it was feasible, just underexplored.
It was feasible.
Yeah.
It wasn't a question of existence anymore. We knew how to do it. There were like several flavors between TFHE and CKKS and there's like BFV, we call it BFV, but it's actually, there's B, there's FV, there's BV. There were kind of variants, but today we call that like BFV. There was also BGV. And so it wasn't possible before actually doing the bootstrapping, the programmable bootstrapping with TFHE to have a super low latency in computing. Because all these other constructions, they basically, the latency is terrible, but they can batch massively. So in amortized time, it looks good, except that it takes forever. Well, it takes a long time. And so you have to instrument that differently. But yeah, I kind of reached out to Rand saying, hey, I found new results on programmable bootstrapping. I think, I think that could be something that boosts the practical use of FHE. Are you interested in like starting a company or something? At the time, it was like selling snips to Sonos. And then we discussed, we kind of started to meet people. We also looking at the tech itself. And what was very funny was at the time in my mind, the main application was like machine learning, neural networks, encrypted AI.
And that was Rand's previous company in the area too.
Yeah, exactly.
That was the only, okay.
So, but I didn't know much about AI for real. Yeah. So I kind of, so it was a dream team from the beginning because Rand came with knowledge and a background very different from mine, but also very complementary. Yeah. And so he's not a cryptographer, but that's fine. I mean, we can. I'm okay with the cryptography side of things, and Rand was like, complementing that ideally with knowledge in AI, but also in business, how to. A great sense of business, and it was a match made in heaven, almost a marriage or something. But it was
well,
ideal.
It is in a way. Being co-founder is definitely
yeah, absolutely,
So I guess like, what's your vision for FHE? Obviously, there are applications in the blockchain space.
Yeah.
Also AI. How do you see FHE unfolding in the next 5 to 10 years?
Oh boy. So to me, I mean, I fully adhere to the vision that FHE is going to be transparent and like kind of automated in the future for plenty of different contexts. I don't think it will be used like systematically. It will coexist. And but I think it's going to be everywhere. And I really believe in the HTTPZ like vision where actually all the internet protocols are revisited and FHE is kind of integrated in there every time it makes sense. And I think it makes sense even for things that we take for granted, like web API calls. There's no reason why you shouldn't hide the request that you're sending. It depends, of course, of the nature of the data and how sensitive it can be. Yeah. But I mean, I don't know, having like a fully integrated FHE solution for that doesn't look like a luxury for certain applications. It looks like something you would need. Yeah.
It should be encrypted end to end by default.
Yeah.
It should be.
Yeah, exactly. Yeah, exactly. And also, I think the main roadblock is like efficiency. And hardware is coming. Yep. But there's such a surge in, there's an exponential blow up in AI right now. Yeah. And so the hardware like is obsessed with AI and everything. So I don't know if you followed like NVIDIA's latest keynote. They announced like Blackwell, which is another like huge platform for machine learning. But FHE it can be very beneficial for FHE as well because essentially we need FHE as it happens. You need to compute in a massively parallel way. So and it's like simple algebra. So it's just like vectorized operations that you want to do in a massively parallel way, and that's like very very convenient when you look at these new execution platforms. So it looks like again a match made in heaven. So we're gonna surf
Yeah.
on that.
I think the timing is really good.
Yeah,
There's a lot of money, interest in AI.
yeah,
FHE is bringing a lot of value.
yeah,
So
yeah,
yeah,
absolutely.
um, very cool. Could you maybe talk a little bit more about blockchain, why FHE makes sense in the blockchain space?
Yeah, the problem with the blockchain from day one, right, was the fact that it's fully transparent and everything is like auditable, but people didn't think that it could be auditable cryptographically.
Yeah,
It was more
yeah,
like, okay, let's just look at the values, and then the blockchain basically makes it trustable. You
yeah,
cannot like change anything in the ledger. So it builds a notion of trust, but there was no confidentiality whatsoever. So FHE is going to give that ultimate power to a blockchain of like hiding data on chain. The only alternative up until now was to have like this data off chain and then prove things on it, like using zero
yeah,
knowledge.
yeah,
But with FHE, you can now compute on chain and encrypt values and have encrypted states on chain, and it's going to be a transformative. It's going to be transformative for the blockchain. There is no doubt about that. But it's very. I mean, it's one thing to work on the technology, being a technology enabler for that. I think it's a very different thing to actually build solutions for use cases.
yeah,
Um, and it's impossible to grasp all the ideas out there. I think builders know what or will know what to
yeah.
build on top of that.
They will find the opportunities.
Yes.
Yeah,
Yeah. So I think they will. I mean, we can all have ideas how to create new user experiences and
yeah,
crack problems, but in the end, I think anyone is capable of I think seeing. I mean, anyone developing on the blockchain is capable of seeing how to use FHE for the better. And yeah, but plenty of ideas out there. Yeah, we're discussing liquid voting yesterday.
yeah,
There was this other idea also, which has to do with I don't know how to call it, like automated watchers or bots. I don't know,
okay,
like automation. Um, like typically if you take FTX, right? So everything that happened,
yeah,
right? And you put everything that has to do with the accounting. FTX pushes encrypted
yeah,
on the blockchain,
yeah,
right? So you still have to ascertain the authenticity of the source data, but suppose that you're a company or whatever, right? And you push everything that has to do with your balance sheet, you put encrypted on the blockchain,
yeah,
right? And then you have typically a bot that actually is doing some kind of accounting
yeah,
task on it that basically outputs zero, everything is fine, or fraud.
yeah. If there's a hole in the balance sheet, and
Yeah.
yeah,
Like you can extract the algorithm that tells, given
yeah,
a certain balance sheet, is everything compliant to the law
yeah,
or not? And so it could output fraud, or even like fraud type 1, fraud type 2, fraud
yeah,
type 3. But that's all. That's
yeah,
all the information that you're extracting. And so it goes through the threshold decryption, because you just developed the smart contract to do that. And every time a new value is being pushed, because the balance sheet is being updated over time,
yeah,
the smart contract triggers and outputs this public information 0, everything is well,
yeah,
or fraud type 1, fraud type 2.
yeah,
So if you do something like that, I mean, FTS is just a stupid example, but it would have been good to know at the time if there was a problem, even if you
yeah.
wouldn't know the details. But
So right after when FTX happened, all the exchanges started posting this proof of solvency, right? But this should technically, yeah, be on the blockchain since day one. But you also don't want to reveal everything about your business, right?
right,
Because that could leak
exactly,
information about
exactly,
any competitive advantage that you
absolutely.
have, right?
But
So
FHE
yeah,
kind of isolates data mathematically
yeah,
from the computation part. the data part, the computation part, and this isolation. And so they coexist in isolation, and so you can like appropriately, customize the level of information that you want to make public and keep the rest completely private. It may even become something of a regulatory obligation in the future. I don't know, but this is the kind of stuff that FHE allows you to build. So it could be also something, I don't know, useful for in many contexts to do that, like having automated bots on the blockchain that actually trigger events, but protect the source data.
Yeah, I really see this being necessary because if we want to bring in more Web2 practices, right, you need a layer of confidentiality, but you still want to use blockchain as this trust layer, right?
Right. Yeah.
And yeah, I think solving understanding confidentiality is not just about privacy. I think it's just really about enabling some of these more novel use cases, but also more sensitive cases. They're very practical for businesses, enterprises, institutions.
Yeah, absolutely. I'm thinking even for I don't know compliance. I mean for banks typically. Compliance with like anti-money laundering laws, things like that, which is a nightmare for them. I mean, it's very complicated for them because they cannot. I mean, it's hard to do KYC without breaking privacy laws. I mean, there are plenty of trade-offs in there. So I think this this space really needs a disruption, like a technical disruption, and I think FHE can be a big part of that.
Yeah, absolutely.
Yeah.
And that's why we're super excited about this recent developments, breakthroughs, and we really think it's kind of like the natural next step where blockchain will evolve into. Just having the ability to store public and private states.
Exactly.
Just the way you would build in Web2, essentially.
Yeah, exactly. Yeah, exactly. And I think in terms of next steps, there will be at some point also the kind of a merge between ZK and FHE. ZK in the sense that ZK in the sense of provable correctness of execution. So you kind of, because right now we need a consensus between the validators, to ascertain that the amorphic execution was done correctly. But the idea is instead of replicating the same amorphic computation, which already takes resources, there's just one entity that does a job, but generates a proof along the way, and gives you the output together with that proof, and everybody can just validate the proof effortlessly.
That'll be the dream. Yeah, ZK FHE.
Yeah, but it is coming. I mean, it's the question of existence isn't there. We know it's feasible. It's actually how efficient can it be.
So you guys did a poster recently. I think the benchmark was 48 minutes to generate a ZK proof of a bootstrapping process today. And then there could be hundreds or thousands of bootstrapping that needs to be proved. In a transaction.
Exactly. So we're getting there, but it's we still have problems. It's basically science at that point. It's not even in the engineering cycle where you try to productivize these ideas, but it's gonna get there. And there's at Zama we have a team, the Zama Labs, who's working on that and other things as well. But and we think it's gonna be actually the holy grail is probably correct FHE. It's not just FHE alone, but probably correct FHE, and that's probably something that the Web2 will need as well for adoption. I mean,
because today, a company, if you compute on top of another company's private data and you don't provide some kind of ZK proof, then how can I really trust you? It's the same problem.
Exactly.
In terms of Holy Grail, there's this concept that I heard. I think it's called functional encryption or decryption, where you could decrypt a ciphertext without needing another set of private keys.
So that's another thing that would be transformative as well. Right now with FHE, So the way it works, you have your homomorphic Ethereum virtual machine, and then you run the smart contract. At some point, you need to decrypt, right?
Yeah.
You need to do like proxy re-encryption if you want to view like homomorphically encrypted data, or you need to decrypt on the fly during the execution. And for that, we have the threshold decryption kind of mechanism.
Yeah.
Where the shares, I mean, basically the secret key, the FHE secret key is like thresholdized across the validators and so on. But it's, I mean, functional encryption would allow one to get rid completely of that part. And the way it would work is, so what is functional encryption? Functional encryption is, for instance, Remy, you see a ciphertext coming in, and you're being given a decryption key, but that decryption key comes with a twist. There is a function inside. And so when you apply the decryption procedure, you don't access the message, you access the function, which is in your decryption key, applied to the message, right? So you see an encryption of M coming in, you have a secret key containing F, and what you get is F of M when you decrypt. But you don't get M, you get F of M. And there's a kind of a master key that can create decryption key for any kind of function. So that's the concept of functional encryption.
It's some kind of event-driven decryption. If I understand correctly.
There's no real notion of time at this point. It's just a notion of like logical dependency between what you see and what is available. So you can have like privileged access to access the full message or part of it, or like transformations of your message. So having the master key, I can like distribute to certain entities some powers to access the message in certain forms, right?
Interesting. So basically, you can create some kind of access control.
Yeah, exactly.
But that's more modular. So it's not a global key that decrypts everything. It's more specific keys for specific cases.
So there's still like this big master key, which is the center of of cyber threats.
Yeah.
But if you get rid of that for a minute, what is interesting is that we could use that to do homomorphic computing as well. Basically, we would split the homomorphic computing in two parts, F1 and F2. You would do homomorphically just F1. You would have an encryption of F1 of X. And then I give you a decryption key with F2 in there. And then you decrypt and you get like F2 of F1 of X. And F2 and F1 would like do the whole initial processing that was needed. And it would like self-decrypt. You would have, there would be like no notion of thresholdized decryption, network or anything. So you would have like self-decryptable FHE if we were suddenly capable of mixing FHE with FE. And that would be like super nice to be able to do that.
How difficult is it to achieve that, you think?
Well, right now we don't know how to do that. And also FE is so poor. I mean, the concept is brilliant. In practice, the only function that you can put in a decryption key are like inner product with a secret vector. Or we can hardly go to like quadratic functions. And even when we do that, it's pairing based, so it's not post-quantum. So there's
pretty far.
We're pretty far away from achieving that. But you never know.
It's a cool vision,
It would be.
I guess the holy grail would be ZK-FHE plus functional encryption.
Oh yeah,
that would be the holy grail.
Oh yeah, absolutely. Yeah, that would be amazing to be able to combine the three of them.
Yeah.
I think that would be like a dream come true. But already having FHE is like kind of a dream.
Yeah, no, for sure.
come true.
Yeah,
right?
It's already a big step forward.
Yeah. So I'm not really pessimistic. I think we never know. We'll see. We'll see. But I mean, there's like probably years of research ahead of us in terms of, improving FHE and making like more practical, more usable, to mix it with other stuff. So like FE or ZK. I think we're going that route. But who knows how much time it will be
Yeah.
needed to achieve these like dreams. So
Yeah.
we'll see. But we certainly don't need all of that to deploy FHE today and already use it for the better.
Yeah. These are more optimizations down the
Yeah.
line for sure.
Yeah, exactly. Yeah.
Yeah, I think today we covered a lot from the past to projecting far into the future. But yeah, I think it's been great really just having this conversation with you. Yeah, I really appreciate the time that you took today.
Sure. My pleasure.
Yeah.